So what we're going to learn now is about the ideal gas law. Okay, so the ideal means that it talks about the perfect gas. So if you remember the kinetic molecular theory, the ideal gas is very small. It hardly takes any space. There's no attraction or repulsion, no hydrogen bonding, no IMFs. Okay, so if it were a perfect gas, you're going to be able to get a universal law. This universal law is one formula that can derive all the other formulas about gases. Okay, it's a law that tells you a formula that predicts how gas molecules behave. Okay, so the ideal gas law, the formula is equal to is PV is equal to nRT. So this gas law shows the relationship between P, V, and T for real gases. That's what that does. So, for example, if I know the pressure of a gas, and I know the moles, and I know the temperature, R is a constant, I'll tell you about that later, you know that as well, you can predict how big your balloon will be if you knew all of these three. If you knew the pressure and the volume, and the moles and the R, you'll know that's a constant. You can predict what temperature it will be. So you know 5, 1, 2, 3, 4 of them, and you'll know the fifth number. Okay? So first, I'm going to go ahead and derive the formula for you. Where does it come from? Well, it comes from all the other laws that we learned. It's like a combination of all of them in one. Okay, first, let's talk about Boyle's law. So Boyle's law has to do with volume and pressure. Our vice president has Boyle's, if you remember that as a mnemonic. So volume is proportional to pressure, but it's proportional to the inverse of the pressure, so 1 over P. If you remember, it's the only one that goes down, right? So we have to take the inverse of it to make them proportional to each other. The symbol right here, that just means proportional to. Okay, they're related to each other, not exactly equal to each other. If these volume goes up, 1 over P will also go up. They're proportional to each other. Now, Charles' law, Charlie Brown is on TV. So volume is proportional to temperature, not the inverse of temperature, direct, which means if 1 goes up, the temperature goes up, it gets hotter, the volume gets bigger. Guy Lucé uses toilet paper. Okay, so pressure is proportional to temperature. If you heat it up, the pressure goes up. Avogadro's law is moles, which is symbol is N, and volume. So as you add more moles, it's proportional to the volume. As moles goes up, the volume goes up. Okay? What you do now is you add all of them. The proportionality sign is on this side. P and V is on the left side of the proportionality sign. P and V is proportional to N and T, right? N and T are on this side in the numerator, and the P is in the denominator. You see that? Okay, so the P goes here. As you can see, this P is the same as this P. So if you just put it over there, it's the same thing. So I'm going to go ahead and erase it, okay? So all I'm doing is that the P is proportional to these two. And inversely proportional to the V. And you can see it almost looks like the formula here. And remember, all I'm doing is I'm just deriving this equation, okay? Where does it come from? Okay, so now that it looks almost like that, what I will do is I will then plot this on the y-axis and plot this on the x-axis. Okay, so the reason I'm doing that is so I can get a straight line, because y is equal to mx, and the y-intercept would be 0. Okay, so the proportionality sign becomes equal. These are equal to each other if I multiply it by a constant. Okay, so now I'm going to plot. All I have to do in the lab is take a balloon, right? figure out how many moles I have inside the balloon, and multiply it by the temperature in the room, that says 25 degrees Celsius. Okay, multiply that and plug it in on the x-axis, moles and temperature. Then I can measure the pressure inside the balloon, and I can also measure the volume of this balloon, multiply them and get the y-axis. Change it and keep getting some data. Okay. If you plot this, you're going to get a straight line because they're directly proportional to each other. Okay. When you plot it, you will get a slope, which is m right here. Okay. That slope is pretty much r. So if you rewrite this equation, there's the PV, which is, okay, y is equal to mx, right? The y-intercept is 0, so I'm not adding it. On the y-axis, the y-axis is PV. The slope is r. We call that, it's called the universal gas constant because the slope is not changing. And x is equal to nt. And you just rearrange it and it looks like this. So what is r? R is called the universal gas constant. Okay, universal because it's for, all the laws. It's for gases. Constant because it doesn't change. It doesn't change. It doesn't change because the line, which is the slope, is the same here. The slope is the same here, here, and here. If there's a straight line, right? It is a straight line. I just wrote a crooked line. So the slope is not changing. So this r is constant. And you can actually find it, okay? Remember, the slope in this spot is the same as this spot, is the same as this spot. Okay, so what we're going to do is we're going to solve for r. Okay, first, you should remember that r will never change. Because the slope here is the same as the slope here, okay? So what we're going to do is we're going to solve for r at STP. Okay, remember standard temperature and pressure. Temperature is 0 degrees Celsius and pressure is 1 atm. Okay, so r is equal to rise over run, because that's the slope. Rise is PV, so r is equal to rise, which is equal to PV over run, NT. So all we have to do is pressure, volume, moles, and temperature. Okay, so if we're going to solve for r at STP, standard pressure is 1 atm. Standard temperature is 0 degrees Celsius plus 273 equals 273 Kelvin. Okay, now it's up to us how much moles we want to put in a balloon. Okay, let's pick 1 mole because it's easy. So 1 mole, and let's think, what is the volume of that 1 mole? So that volume is called the molar volume. Okay, so here's a fact. If you take a balloon and you put 1 mole of any gas and you put it in a room at 0 degrees Celsius, which is STP, and 1 atm, your balloon will be 22.4 liters. So the molar volume of a gas is 22.4 liters, is the volume of 1 mole, molar volume. okay? And it only, of course, in these conditions, which is STP, okay? So if you take a mole of helium gas, let's say, 1 mole of helium, you can do 1 mole of CO2, 1 mole of any gas. It's going to have a volume of 22.4 liters. At these same conditions, of course. Okay, so the molar volume of one mole is 22.4 liters. So R is equal to, go ahead and plug that in the calculator. I got 0.0821. Okay, so the units, ATM and liters. I'm going to put the liters in the front because that's how they have it in the book. Liters times ATM, and then Kelvin times mole. So this is what R is up here. You see this R? R is equal to 0.0821 LATM Kelvin moles. Okay, which is equal to the slope. So what's the slope at STP? Let's say over here, 0.0821. What's the slope in Alaska? 0.0821. What's the slope in a hotter condition? 0.08201. 0.0821. So this R will never ever change because it's a straight line, so the slope doesn't change. Okay? But you have to be careful. The units have to be these. If you change the unit, of course the number will change. Like 1 ATM, if you use 760 mmHg, of course the value will change, but it won't be ATM anymore. It'll be liter mmHg. So make sure that you use these units, okay? Okay, so how do you use it? It's such an easy formula. If they gave you, so the formula is P V equals nRT, right? So if they give you P is 1, you just plug it in, 1.0 ATM. V is 2.0 liters, so you plug that in. How many moles? So N is missing. That would be your X. What is R? R will never change. It's always 0.0821. 0.0821 LATM, and you have to write the units of this all the time. Okay? And the temperature is, oh, I'm sorry, that should not be mole. Kelvin, let's just Kelvin. I just made easy numbers. 3.0 Kelvin. That's pretty cold. Okay, I was just making it 1, 2, 3. Okay, so how many moles is that? Which is really powerful, right? If you have these conditions, how many moles is in the container? So plug that in the calculator. You're going to divide both sides by 0.0821 and 3. So it'll be, divide both sides by these two. Okay, let me just do that now. Okay, so you're dividing by 0.0821 LATM K mole and 3.0 K. Divide that on the side, 0.0821 LATM K mole and 3.0 K. Okay, so notice this K unit cancels with this unit. The L cancels with this L. The ATM cancels with this ATM. And you're going to end up with 1 over mole, which is equal to moles. Because when you divide, you multiply by the reciprocal, so you just get moles. So X will be in the unit of moles. Okay, because it's the only unit left over there. Do you see that? Okay, so when you plug it in, you go 1 times 2 divided by button, 0.0821, divided by button again, 3, which is 8.12. So what that means is you now know how much moles you have in that container by measuring all these things that you can measure outside of it. And the moles, you can't really see it, but now you can get it, which is very powerful. Okay? Again, if they don't give you 1 ATM, let's say they gave you 760 mmHg, you have to convert this to ATM, okay? Because if you don't, and then plug in ATM, if you don't convert, you're going to get the wrong answer because the ATM or the mmHg unit will not cancel, okay? So why is it called universal? From one formula, it's like you can get all the other formulas. Okay, let me show you. If you change, if you keep moles constant and temperature constant, if you keep these two constant, okay, this is what happens. What I'm going to do first is solve for R, okay? So divide by NT on both sides. So R is equal to PV over NT. Okay, which is equal to PV over NT is always going to be equal to PV over NT, right? So if they're both equal to R, that means they're equal to each other. P1V1 and 1T1 is equal to P2V2 and 2T2. So you can have another formula that you've never heard of for things changing. If you have these numbers and you're missing one, you can solve for it. Okay? If you keep N and T constant, you keep these two constant, that means if this is a 1 and that's a 10 and that's a 1 and that's a 10, they cancel each other out, so they're gone. So now you have P1 V1 is equal to P2 V2. So by holding two of them constant, you just derived Boyle's law using the universal gas law. That's why it is so universal. Okay, let's do it again. So doing the same thing, P1 V1 over N1 T1 is equal to P2 V2 N2 T2. Why don't we hold something else constant? Why don't we hold pressure and moles constant? If you hold those constant, they disappear, right? Because they cancel each other out. So what we have is V1 T1 is equal to V2 T2. You just derived Charles's law using the universal gas law. Okay, and you can keep doing the same thing to get the other laws.